Hey everyone, welcome back to another fun math video on my channel. Today we're going to be talking about a totally interesting topic which also connects to last week's video. So if you really want to get a deep understanding of this, then I suggest you should watch the previous video I put, which was arithmetic sequences. This week we're going to be doing just that, but with a little twist. It's arithmetic series. Well, they sound so similar, you might be wondering, what's the difference? Well, first of all, arithmetic sequence is a sequence of terms with a common difference between each term, meaning it's either increasing, decreasing at a constant rate, or it's just the same. In other words, an arithmetic progression. An arithmetic series is just the sum of all the terms in an arithmetic sequence. Now, this can be either infinite or finite. For example, if the arithmetic sequence is a finite sequence, then your sum is obviously finite. If the arithmetic sequence is infinite, then it gets a little more complicated. Now, infinite arithmetic series does not have a sum because the sums, they just keep getting larger and larger with no end or they don't really seem to be approaching a number. So let me give you an example. If I were to add 1, 2, 3, and 4, or instead of starting that way, let's do this. Let's say I had the sequence 1, 2, 3, and 1, 2, 3, 4. That's an arithmetic sequence. Now the series equivalent of that would be 1 plus 2 plus 3 plus 4. And this is 10. So the series is 10 in this case, the sum of the terms in an arithmetic sequence. Now, if I were to say this is your sequence, 1, 2, 3, 4, but this time it just goes on forever, never ending, then the sum would be 1, 2, 3, 4, and it could go on forever. Now, if we were to add 1 and 2, we'll get 3. If we were to add 1, 2, and 3, we'll get 6. Adding 1, 2, 3, and 4 gives us 10. Similarly, 1, 2, 3, 4, 5, 15, and this keeps going on. So you can see the sums, they don't really stop. After every partial sum, it only increases. It doesn't decrease. From 3 to 6, it's an increase. From 6 to 10, it's an increase. And from 10 to 15, it's an increase. It'll keep increasing, increasing, increasing forever. So there's no limit to where it reaches. It can keep going on as high as it wants. In other words, this sum doesn't have a limit. It's undefined. Now, as you'll see in a future video, geometric sequences and infinite geometric series has a sum. Not all, but some of them do. In this case, it's an arithmetic series, and no infinite arithmetic series has a sum. Okay, so let's get started on some not so simple problems. If I were to add 1, 3, or actually, let's not do that. Let's say 2, 4, 6, 8, 9, and this will go until 48, let's say. Obviously, this is way too many terms to just add out by hand. You're going to add 2 plus 4, then 4, 2 plus 4 plus 6, 2 plus 4 plus 6 is 8. It's too many, way too many. Instead, there's a neat little trick you can do here. And this trick can come in very handy if you understand how to do it. And this is where I'm going to show you how you derive the formula of the sum of the finite arithmetic series. Now, to start off, let's let this equal s. Then I'm going to rewrite s again, but this time, instead of starting from 2 and going to 48, I'm going to start from 48 and go to 2. So it's the reverse. 46, 44, 42. Oops, I made a mistake here. That was not 9, it's supposed to be 10. 9 is not an even number. Okay, so 40, and this will go to 2. So basically all I did is took the series and flipped it around. Now, even if you flip it around, it has the same exact value. We know by the commutative property of addition that No matter how you add things, it'll always have the same value. So essentially, this is just flipping it around. Now what I'm going to do is this. I'm just going to go ahead and add these two equations, just like that. No tricks, no magic, just add it. On the left side, it's 2s. And on the right side, 48 plus 2, 50. 46 plus 4, 50. 44 plus 6, 50. 42 plus 8, also 50. 40 plus 10 is 50. And you can get a bunch of 50s until you do the last 50. So it's all 50, 50, 50, 50. Now, this is much, much, much easier to add than the previous num. So for example, if you were to add 50 plus 50 plus 50, that's the same as adding 3 50s, or it's 3 times 50. So adding 50 plus 50 plus 50, let's say n times, is the same as doing n times 50, because there's n 50s there. Now the question remains, how many 50s are actually here? How many? Well, the value of each of these terms is different from the original sequence. However, changing the value of the term doesn't change the number, how many terms are actually in the sequence. So let me show you a quick example. If I were to say 1, 2, 3, 4, right? Now, if I just add 22 to each of these, it'll be 23, 22 plus 1, 23, 24, 25, and 26, right? Now, I changed each of the terms, but in both of these, there's still 4 terms. I'm not changing how many terms there are. So if we want to find the number of 50s here, it's the same as finding how many numbers are in this series right here. Let's try finding that. We have 2, 4, 6, 8, all the way to 48, right? Now, remember I just said, whatever you do to each term of the sequence, it doesn't change how many terms there actually are in the sequence. So, to make this simple, we know all these are even numbers, so why not just divide by 2? Get 1, 2, 3, 4, and this will go on to 24. Now, we know that from 1, if you're counting to any number, it's the number of terms is that number that you ended with. So from 1 to 24, there's 24 numbers. Now we found how many 50s there are. There are 24 50s. So that means I can write 2s is equal to 24 times 50. And finally, dividing both sides by 2 to get rid of this 2 here gives us s is equal to 12 times 50, or 600. And look at that neat and easy way to find the sum of this. Now, trust me, if you were actually thinking of adding all these up, just remember, in math, there's always a better way. Even if you found the best way, there's always a better way. Just remember that. Okay, that was decent. Now, let's do something a little harder. Let's say I wanted to find this sequence. 1, the sum, 1 plus 5 plus 10 plus 15 all the way until 75, right? Well, I'm just going to use the same trick as I did before. I'm going to reverse the series, and I'll get 75 plus 70 plus 65 plus 60, and that will go all the way down to, oh, oops, actually, I should have started with 0 here, because that's what would make it an arithmetic sequence. Okay, now it makes sense. Then I'm going to do the exact same thing as before and add it. 2s on the left side. Then each of these terms just become 75. and 75, and it's all just 75s. Now, in case you didn't observe in the beginning, when you add the sequence and its reverse, which is basically doubling it, you'll get the same number every single time. And this number, if you look carefully, is actually the sum of the first term and the very last. Even here, 50, you can get it by adding 48, or 2 and 48, right? It's the sum of the first and last. But I'll show you soon why that is actually true, because it's an assumption right now, but you have to prove it's true, right? Okay, first of all, let's tackle this. 0, 5, 10, 15, 20, 75. Now this is a little harder to find how many numbers there are. We could divide by 5, but I'll also show you another way to do this. Now, sometimes you cannot always divide by number to get things like 1, 2, 3, 4, 5, 6, 7, 8. Yeah, you cannot always do that. For example, if you have 1, 3, 5, 7, 9, what would you do here? You can't divide by anything. You can't get this to be 1, 2, 3, 4, 5, 6, 7, 8, 9 the way you want it to be, right? Some of these numbers are prime, so they don't really have any common factors with the other ones. So what you can do is take it as an arithmetic sequence. Arithmetic sequence, yeah. Now remember, how do we find the nth term of an arithmetic sequence? Well, let's see. We can do that by taking the starting term, in this case, it's 0. The common difference, in this case, it's 5 into n minus 1, and that'll give you the nth term, right? Now, let's say to find how many terms there actually are in the sequence, we'll just leave this as n, but we know the last term 75. So let the term number of this term, let this be the nth term. We want to find what the value of n is. So we use this right here. This is a general form for any term, and since we want it to be 75, we'll let this equal 75. Then the 0 is just 0. We can ignore that. 5n minus 5 is 75. Excuse me. 5n is 80. And n would just be 16, right? Ta-da! We found it. There are 16 terms in the sequence. See? Just that simple. That's a neat little trick to remember anytime you need it, because you know how to find the nth term of an arithmetic sequence, right? Just use that. Now, we found there's 1675, so the right-hand side just becomes 16 times 75, and the left side is still 2s. Then we finally divide both sides by 2 to get 8 times 75 on the right-hand side. And 8 times 75 is 600 again. Wow. So, interesting thing, honestly, I made this up on the spot, and it's actually quite a coincidence, even for me, that we got the exact same number both times. Yeah, so 600, we again found the value, and this time we didn't actually divide. We just used what we know about the nth term of an arithmetic sequence and found how many terms there actually are. And this is a useful thing to remember. Now, we're going to generalize this approach to all sequences. All right, let's have a sequence with term number 1, or first term is equal to A, and common difference is equal to D. Then the sequence would be A, a plus d, a plus 2d, a plus 3d, on until for some arbitrary a plus nd. Or actually a plus, if the series a plus n minus 1d, right? Yeah. Which denotes the nth term of a sequence. Now, we're going to do the series and add it up. S is equal to a plus d plus a plus 2d plus a plus 3d, and it'll go on until a plus n minus 1d. We're going to just reverse this series, and we'll get a plus n minus 1d plus a plus n minus 2d. And I'm not going to write out everything. I'm just going to go off until a plus 2d, a plus d, and a, right? Then what do? We add these two equations. On the left side, we end up with 2s. On the right side, this is what we end up with. Now, let's see. The sum of the first and last terms in this case is 2a plus n minus 1d. Interestingly, when we add up all the terms, we get that exact same. 2a plus n minus 1d. So now we generalized this to using arbitrary variables and showed that every time the number that we end up with here is the same as the sum of the first and last term, right? So it means we don't have to write the entire series, reverse it every time and add it. We can do it just by adding the first and last terms and finding how many terms there are in the series. That reduces our time much further. Now we're going to add. Actually, let's just leave it here. We'll leave it right here. Do nothing else to this, because all I wanted to show is that the sum of the first and last terms is what we end up with every time when we add the series, when we double it. Now, obviously, here there are n terms. Now, this time, I'm going to show you something with general. I'm not even going to write out the entire series. So let's say term number 1 is a again. Common difference is d, and the number of terms, let that be n. Starting term is a, the common difference is d, number of terms is n, and also one more thing. Last term is r. Let the last term be r. Now, if we just double the series like we did, then using it, we'd get the sum of the first and last term, remember? And that's a plus d. But this is all, we have to multiply this by the number of terms there are. And we know that is n. So we get this. And the sum of the series, well, that's just n into a plus d over 2. As simple as that. This is the simplest way you can write the formula for an arithmetic series, where a is the first term, d is the common difference. Oh, whoops, not dr, rr. I'm an r here. Okay, yeah, now it makes more sense, isn't it? So, actually, if you notice, we don't even need the common difference for the sum of an arithmetic series. We can do it without it. And interestingly, a plus r over 2, that's the arithmetic mean of a and r, meaning it's the average of the first and last term. And that makes sense because if you average the first and last term and multiply it by the number of terms, you should get the sum of the series. And if you really think about it, it should make sense. It looks symmetric, right? And there you go. That's the conclusion I wanted to share with you today. Thank you so much for listening to this video, and please subscribe to my channel and give this video a huge thumbs up. See you next time in a more interesting topic than this one. Bye bye.